Hello everyone and welcome to the afternoon session, the last talk of today. We thank everyone who has joined us, especially Dr. Chakraborty to join us and agreeing to give a talk. So I would like to ask Dr. C. Lakshmi, who is the club coordinator for CMIT, to introduce him formally. And this will be the last talk for today and I hope everyone will enjoy. So over to Dr. C. Lakshmi.
Thanks. The third and last speaker for the day one of this symposium is Professor Kalyan Chakraborty. Professor Kalyan Chakraborty is a number theorist working with various aspects of this field. He is currently the director at the Kerala School of Mathematics at Kozhikode, Kerala, and a professor at the Harish Chandra Research Institute, Allahabad. He did his PhD in number theory from Harish Chandra Research Institute, Allahabad, under the guidance of Professor B. Ramakrishnan. Professor Chakraborty has held visiting positions in several esteemed universities and research centers from the international institutes around the world. He is also the chief organizer for the International Conference on Class Groups of Number Fields and Related Topics, which happens every year at HRI. Over the years, he has published many research papers in analytic, algebraic, and computational number theory and has collaborated with many. He joined as the director of Kerala School of Mathematics just 2 weeks back. I am grateful for his valuable time for agreeing to give a talk in this maths club. Few months back, he visited IISER Thiruvananthapuram and had given a wonderful talk about his recent research work. With my student Sunil, I could generalize one of his paper, and it is a preprint now. I wish he visits IISER TVM more often and we could collaborate more. And he has guided several PhD students. He is also a mentor for several postdoctoral fellows. He is also quite friendly with all students. And today we are very glad to have him as a speaker at CMIT's Foundation Anniversary. And his talk is titled Cryptography, the Science of Information Technology. Professor Chakraborty will talk about this area, which combines the techniques of pure mathematics with that of computer science from a historical perspective.
Yeah, so thanks, Dr. Sri Lakshmi, for such lovely introduction. I'm really happy to be here for this maths club. And I congratulate the club also for becoming 2 years old now. And I wish a very, very long journey for this club. And this is a very nice thing, you know, the students and all on a weekend, you can get together and hear some, you know, some light kind of a maths talk. So I'm grateful to Professor Sri Lakshmi and the club organizers for giving me this opportunity. Well, I mean, since I'm just out from quarantine, just 2 days back, joined his office. You know, this is a slide which is already ready. I have given it to many places, people to enjoy. So this is a very, very introductory talk. I mean, people who are already working in crypto or something like that, you know, close to that area, they will not find anything new. But you know, it's just fun to sit for an hour and enjoy the beauty of mathematics. And that's the sole aim, I think, for this kind of here thing. Have a cup of coffee or tea with you, and in this kind of pandemic time where we are mostly confined at home or our own institute, can't travel here and there, this is a nice way to keep in touch. Okay, so thanks a lot again, and let me start my presentation. Yeah, so I'll request Sri Lakshmi to keep your mic on. If in case there is any trouble, you can just tell me.
Okay.
Okay, thanks a lot. Well, so this is the title, Cryptography, the Science of Information Security. So all of you have heard about it and might be knowing already. So I'll just start from a very, very basic things. And as I told you, that just sit down and enjoy these slides, which are mostly historical pictures and some mathematics. Okay, so this is the way that I have planned the talk. I'll start with some introduction, some overview. I'll give you an interesting puzzle. I know it's not a puzzle. Most of you will be able to solve it immediately, but then we'll come back at the end for that one. Then there is this what is called public key cryptography. There are two types of this crypto systems. I'll just shed some light onto that one. Some examples of some functions which are being used. Then some mathematics will come, and then I'll come back to that puzzle and then talk a little bit about what is going on there in integer factoring. Okay, so let's begin the journey. It's a light talk, as I told you, a lot of pictures you will see. So what is cryptography? Okay, so we should always, when we study something, it's good to go back to the history and try to find out from where probably it has originated, and how we have progressed so far, where we are right now. So the word has a Greek origin, and most probably was used around 1900 BC by Egyptians. Okay, so it's a combination of two Greek words. The first one is crypto, that means secret or hidden, and the second one is graft. Graft, we all know, I mean, it means writing. So we have cryptography, so crypto and graft. So that means writing secret code, secret, so, writing something which is secret. Secret means, you know, whenever we talk about secrecy, we try to generate things which is not easily possible for others to understand. So that's always we have to keep into mind. So here is a formal definition, if you wish, of cryptography. So it's the science of converting a stream of text into coded form in such a way, I mean, some cover, coded means some kind of secret cover is there on the top, such that only the originator, person who is originating that one, or writing that one, or receiver, the person who is receiving of the coded text, can decode. Okay? Nobody else. So that's the aim. That's the aim of this cryptography, that some text is originated. Some way you have to put a cover on that one, so that in between, when it is traveling, nobody else will be able to uncover it. And when it goes to the receiver, there is some process to decode it. Receiver gets it. Okay, so in other words, cryptography is the science of information security, which all of us know that how important now in the present situation, this security of informations. Now, cryptology is a much broader subject, which is cryptography is just one side of that one. There is another side called cryptanalysis. So cryptanalysis is the science. So here we talk about writing protocols, making a code, and the other side it tries to study how to break it. So breaking the code. So that's cryptanalysis. That's another side. We can talk about little bit about that integer factorization part, which will set some idea that how this breaking part takes place. Okay, so we'll start with objectives. So what we have done so far, just I told you that what is the meaning of cryptography and formal definition of that one, and then we go to the objectives. That when you form a cover, a code, what should be the objectives of that one? So the first objective is the most important one, is confidentiality. Okay, so that's I told that the information cannot be understood by anyone for whom it is not intended for. And then data integrity. So that is the first part. Data integrity is that information cannot be altered, either in storage, because there will be you write an email, it goes to the server, there it is there, chance of breaking it, and then it goes out and it transits. So it should not be, one should not be able to alter it without getting detected, right? And then authentication. So confidentiality, then you have to take care of this integrity part, and then the authentication part. The sender and the receiver can confirm each other's identity. Okay, so that's another important part, and the origin and destination of the information. So each other's identity and from wherever it is being originated. That should be possible to get it from your protocol. Okay, so that is what is the authentication part. And aspects. So we saw the objectives, and then what are the aspects of applications? Of course, not going too much. People all know the applications. And we all know now that mathematics, modern cryptography, heavily depends on mathematics. and the usage of digital systems. That's computer science. So mathematics plays a big role, and then mathematicians use various tries to use a lot of this mathematical tools to make it stronger and stronger. And I mean, these days mathematicians are also good in writing algorithms and all, but then at the end you need the help of really the digital systems, computer scientists, to really make it a complete protocol. And people need privacy, so application part, there's no need to shed much light because we all know. And security while communicating. So we need privacy, and of course we need security. And cryptography provides methods. This mathematics gives you that methods and techniques for a secure communication. And of course, the technology has progressed immensely, and more and more we are depending on electronic systems. Even now, you can see that even the lectures and all conferences are all we are depending on these systems, and all the important meetings, which is supposed to be not going out at all. The discussions and all are through online now. So the importance of this security part has increased manifold. So is the use of mathematics, use of modern computers and computer scientists. So this is the era where a huge demand is there for people who can use their mathematics for helping this forming these protocols, and theoretical computer science who can understand that and make it as a protocol. And of course, in military, as you understand, that in military applications also a lot of sensitive informations are there, which needs to be kept secret, and they use cryptography for that. So that was the aspects, and there's applications. No need to say anything about the application part, and what the terminologies. So these are very, very, as I told you, very, very introductory talk, and people who know, I just apologize to them that might be thinking that it's just child's play, but it's okay to have sometimes very fun kind of a talk. So plain text, the first one, as I was talking about, the text, the human language or normal text. That's the first starting point. And then you need to encrypt it. So plain text, there is some script, which is normal human text, and then it gets encrypted. So it is the process of converting what is encryption. It is the process of converting a normal text or data into information, into some text which is gibberish text, which should not be, the other should not be able to understand from it the original one. So that text, when it gets converted, it's called ciphertext. Okay. So plain text, then the lock is put onto that one, and it becomes a ciphertext. It's called ciphertext, and then it travels through insecure channel, travels from one place to other place, and then it goes to the receiver, and the decryption takes place there. So it is the process. What is decryption? It's the process of converting this gibberish text into a normal text or data, and it goes back to the receiver, and the plain text is back there, and the receiver can read that one. So these are the 4 steps are there. There is plain text, encryption, it becomes ciphertext, it goes through the channel, and then it goes to the box where it has to be read, it gets decrypted there, and the receiver reads it. Okay, so usually this Alice and Bob, it's a two party, but it could be any number of parties. It's just for keep it in a simple form. One uses in this kind of talks where it's a general talk, just 2 parties. So in the basic communication scenario, we have these 2 parties. It's called Alice and Bob. They want to communicate with each other. So here is Alice, and there's Bob. There's a mailbox there, and Alice is sending a script, and a third party is there. So that's why you have to talk about the security part. So a third party is usually called Eve. Sometimes we'll call other name also. But Eve is usually being called is a potential eavesdropper. So eve comes from there, eavesdropper, who wants to do damage, to read. So we'll see what are the things that eve can do. So this is a situation whenever you form a protocol, you have to see that there is one person sending some script, maybe many person, but for the simplicity, just two party we're taking, going there, and then there's a third party who wants to do damage. So Alice wants to send a Bob. So this is called plain text, as you have seen, as we told that this script is called plain text. And then the encryption takes place. So there is a lock which has to be put on that one. It traverses through the channel and it's called ciphertext. And there you have Eve. When the ciphertext is formed and passing through the channel, it gets decrypted when it reaches the destination. And the plain text is back, and Bob can see that one in the mailbox. Okay, so this is the message. The message is kept secret so that to Eve because of the key, because the key is known, then it can be broken. So this is a very simplistic, most trivial kind of scenario that we can think of, and many complications are there. This is the simplest that I'm talking about. The practical situation is far more complicated. Okay, so this is the picture that you have to remember in our mind. So what could be the goals of Eve? What are the things that Eve can do? So there are a few things that I want to point out. Firstly, it's just to read Alice's message. Eve wants to read, and then one doesn't know what are the intentions of reading that, but it could be as in a course as that one, that just to read. And then the next could be very dangerous, that to find the key and does read all the messages that is being encrypted through that particular key, that particular lock. So the Eve might get the key and can now read all the messages. So you can see there is a hammer. So everything is broken. Whatever is going through that particular lock, encryption, and Eve is able to read everything with that key. So then can corrupt Alice's message such that Bob will think that that Alice has sent the altered message actually. So no integrity, data integrity is lost. Like suppose you are asking your bank to pay somebody like $100 or something like that. So it just changes it and just to create damage to you, adds a couple of more zeros, and then your bank account gets debited by that much of amount. And the worst part of all the things that Eve can masquerade, Eve can behave as if Eve is Alice and keeps communicating with that Bob using that channel, and Bob will think that all the messages are coming from Alice and keeps doing whatever actually Eve is asking. These are the few things that comes immediately into mind, but many other things. So the thing is that it could be as bad as the situation allows. Okay, so your lock should be that good that should avoid such situations, and the situation could be as bad as you can imagine if your encryption is not good. Okay, so these are some of the things that the basic aim, how one finds a protocol, creates a protocol. What are the things one has to keep in mind in a very simplistic framework? So a little bit of history, that how this cryptography started. It's always good to look back. So around 2000 BC in Egypt, when this hieroglyphics that is called in actual terminology, if you say this, were used in around 2000 BC to decorate tombs to tell the story of the life of the deceased. Okay, some noble person, maybe some important person died. People wanted to the next generation, next to next generation to know about that persons. So they used to depict it through various pictures on the tomb. But that was nothing to hide, it's basically to know. But through some pictures and all, they wanted to depict how good the person was. So it's basically not to hide, but to make them more noble, ceremonial, and majestic. So that was the first aim, that to show certain things through some symbols. Now there is a Hebrew cryptographic method which records the alphabet. So this is how things went up and up. Which required the alphabet to be flipped, so that each letter in the original alphabet is mapped to a different letter in the flipped alphabet, and it looks different. So ciphertext, it becomes a ciphertext. So this encryption was called Akbas. And one can illustrate, like A could be mapped to Z, B is Y. So just start writing from the other side. And if you want to write the security word, and with using this encryption, then it looks like HVX, FIR, GB. It's very simple, very easy, but people did use these things initially to hide some script that they wanted to send it to their people without the knowledge of the others. So this is called substitution cipher, because the character is just replaced by another character, nothing more than. It's very easy to find out. And there is this permutation cipher, quite a few of them. So like you can rearrange things, rearranging letters like hello world. You can just put hello at one side, world at one side, and start writing like this. So ciphertext will look like that, HWEO, and goes on. But the receiver will be knowing that this is the way it has been done. So that was the key, and this is the lock they used to put it. So around 400 BC, the Spartans used a system of encrypting informations. This is quite interesting. I like this one, by using a sheet of papyrus, leaf, which was wrapped around the stuff. So the stuff was like a cylindrical kind of thing. So just imagine you have a cylinder, and you take this papyrus page leaf, you wrap it onto that particular cylinder with, exact measurement. The receiver will be having that cylinder. So you wrap the papyrus page on that cylinder, write whatever you want to write. You just remove the papyrus paper from the cylinder, and then it looks like it becomes a ciphertext. And then the person who is receiving that one exactly has this cylinder exact. If it's little bit here and there, then the words will get mixed. So wraps into that one and reads that one. So that was the kind of thing that was used. So this is called Skatel cipher, and it's quite nice. Okay, so that's what, when the papyrus was removed from the stuff, the writing appeared to be a bunch of just random characters. And then alphabetical transpositions, which was earliest documented by Julius Caesar, who used in the military around 60 BC. So each letter is replaced by one in the same order, like 5 places. So n is equal to 5. That's the key. That A is shifted by 5 places, B is shifted by another 5 places, and you write it and then send it like that. So this was used. This was used in India also. So each letter was replaced by one n positions away. So the alphabet are away modulo that alphabet size. We have 26. So in India also similar things are used. So suppose this is Caesar cipher. You can like A goes to D, B goes to E, C goes to F. So you can use this is the way it, like you can see A, B, C, D, and then n equals to 3 here. And if A goes to D, B goes to E, like that, Z goes to C again. So if you want to write cryptography using this Caesar cipher with n equals to 3, so your cryptography becomes FUB, so just like that. It becomes this. So these were widely used during that period, and people found it difficult quickly to decode it, and the job was done. Like some order or something like that to attack an enemy at a particular place and other things. So the order used to be sent, because a person will be carrying that one. That person might be, bribed by the other party, so might read that one. So this was one way that widely was used at those days. But today this technique is, as you understand, is very simplistic. All of you will be able to break it very, very quickly. But in those days, not many people could read it in first place. And you can use all kinds of sophisticated examples, like, without preserving any order, you can mix and match and other things. I'm sure people must have played in their childhood days, sending this kind of thing. At least we used to do it, and challenging that, what is exactly written, can you break it? But anyway, we have just a fixed number of alphabets, so this is never practical. So as the computers came, the possibility for encryption methods advanced, and cryptography has expanded exponentially now. It's a huge subject now, and mathematics plays a big role into that one. You will see. Now this is the puzzle, and I know it's not a puzzle. All of you can solve it very quickly, but we'll see the mathematical formulation. That will be interesting. So here, Alice, so the Eve is called Charlie in this case, which is better maybe, because Eve, Charlie is like a common here thing. So Alice is there, Bob is there. Alice wants to send a suitcase. Alice has a suitcase and a lock and key. That's what Alice has. She wants to send the suitcase to Bob in a secure way. There's some valuables are there in the suitcase, so that nobody can see the content of the suitcase. Now Bob also has a lock and key, but these two are not compatible. Neither Bob knows what lock and key is being used by Alice, or neither Alice knows. But they're not compatible. They have no communication beforehand. And how could this be done? Okay, this is very simplistic, but the mathematical formulation is beautiful. We'll come back to this one at the end of this first part, before I go to the integer factorization. Okay, so there are two types of cryptography. Now we had seen some history, some what are the things that one has to keep into mind while forming a protocol. Now let's see, there are two types of cryptography. One is called symmetric key, and another one is called asymmetric key or public key. And symmetric key is sometimes called secret key also. So the encryption, decryption methods, we have these two keys, symmetric and asymmetric. So what happens in case of symmetric key algorithms? That you can see you have plain text, encryption takes place, and the key is either shared or it is already known to Bob beforehand. So you can see the key is shared. Now there is a problem because sharing key might be risky. So the cipher text, and since the key is shared, Bob already knows the decryption thing and he does it. It's a very simplistic. The encryption and decryption keys are known to both Bob and Alice. Many cases it is same, or at least it is known. Usually the encryption key is shared, and the decryption key can be easily calculated from the encryption key. Okay, so this is what is symmetric key. And in many cases, actually, they are same. So you see, look at the history that all the pre-1970 classical crypto systems are symmetric. Okay, so before 1970, everything was like this. I mean, you make various ways to share the key to make it, safe and other things. There are many key exchange protocols are available. So, but this was pre-1970. All the cryptos were symmetric key crypto. Even now, you might have seen when you do some internet shopping and all, you have DESF, AESF, etc. Data encryption standard and advanced encryption standard. So these are symmetric keys. Now there are few disadvantages of symmetric key, as you can immediately understand, that you need a secure channel to exchange the key. Okay, so sharing the secret key in the beginning is a problem in symmetric key. It has to be exchanged in a way to ensure it remains secret. And then every time you do a exchange, you need to have a key. So there are too many keys floating around. Okay, so you might get missed, you might forget. So there are lots of keys will be floating around. And sometimes this is origin and the authenticity, which is one of the part of the crypto protocols, could not be guaranteed. That from where, since both the sender and receiver use the same key, messages cannot be verified to have come from a particular user. This may be a problem if there is a dispute, you see, with bank or with any other place where you want to send the money. Okay, so this is about the symmetric key, and now let's look at the other side, that you have this following situation. Consider the following situation. What is the situation? The situation is that Alice wants to send a message to Bob. That's the thing. But they did not have any prior contact. Okay? Like symmetric key, there is need to be having a prior contact, or at least, should be knowing some information where the key should go. They did not have any prior contract. They haven't agreed on a key. So exchange is not there. Alice doesn't want to send the key through a courier. Otherwise, all the information that Alice sends to Bob may be potentially, may be vulnerable. Now, what is the solution of that thing? How do Alice communicate with Bob? Okay, so this is a solution is this. This is called PKC, Public Key Crypto System, PKC. And what is this public key crypto system? So this is introduced, as I told you, pre-1970, it was all symmetric key. So this is also called public key or asymmetric crypto. So this was introduced in 1970, which actually brought revolution in cryptography, so to say. So here, what happens that plain text is there, encryption takes place, and decryption. So now every user has two keys. Like Bob, Alice wants to send Bob. So Bob has two keys. Bob has a private key, and Bob has a public key. Just excuse me for a second. Yeah, I'm sorry about the interruption. So this was so every user will have two keys. So Bob has a private key, Bob has a public key, and the public key is being known by everybody. So it's easy to send a message, and then Bob uses the private key to decrypt it. This is such a simple solution, but it took so much time to really get that one done. That every user will have two keys, one private key and one public key. So public key is in public domain, just like in a telephone number. Those days used to be a yellow book where the telephone numbers are there for everybody. So so you want to send a message to Kalyan Chakraborty, so you have to just see, Google it. The public key is there. That email address is there, which you can send the person. It comes to the mailbox, and then the person who receives uses the private key to decrypt it. So this is how this public key works. The Alice has a private key. Text gets encrypted. Ciphertext goes through channel and then gets it there into Bob's box, and Bob's decrypts it using his private key. Okay, so the encryption key is public, but it is computationally infeasible to compute the decryption key. So that's a computationally infeasible. So look at this word, computationally infeasible. Okay, in the current situation, current technology. So whatever is known, it should be infeasible. It should be without information which is known to Bob only. So if the password is known or if the private key is known, that is the only way that one is being able to know what is coming to Bob. So it was first publicly suggested by Diffie and Hellman, so at Stanford University, without practical implementation. They had this idea, but then didn't know how to practically implement it. So that was the idea. Idea is beautiful, but then you have to really implement it. You have to write an algorithm to really so that it works. So the most popular implementation of this scheme, this public key crypto system, is RSA. There are quite a few of them. So RSA is the most popular one, and there are these El Gamal, etc. Now, if you compare this symmetric versus asymmetric key, we'll come to RSA. So in symmetric key cryptography, there is only one key which is shared between both parties, which are communicating in a very simplistic way. Otherwise, at least from the shared key, the decryption key will be available. In public key cryptography, there are two different keys. One is public, one is public key. So one can send message. There is no need for using different keys. So not too many keys are floating around. So now here comes a little bit of mathematics, that how one forms this kind of an algorithm. We'll come to RSA, which is a very, very simple example. And first the algorithm, and then very, very simple example. So these functions are called one-way functions. One-way functions means it is easy to compute. Computer will be able to do it without, when you put it without much of an ado. But then reverting it back should be computationally infeasible. Okay, so that's how we call it one-way function. They're very, very useful, and if you quite a few very popular one-way functions are there. I'll just depict here for you a couple of them, but there are many. And it's easy to compute, but difficult to reverse. Like the process of exponentiation. Okay, which just means that you keep on raising to a power, raising a to the power b. All of us know that b times a times a multiplied b times, and then you read it modulo some integer. Okay, so reading it modulo, so you have this a to the exponent b, raising it, and then you are reading it modulo n. Okay, so then so that is a modular exponentiation. It's very easy because computer will do it very easily. But inversion is difficult. How? So, however, if I give you a, n, I give you a, I give you n, I give you a to the power b mod n. This is public. But from here calculating b, so you know a, you know n, you know a to the power b modulo n. So modulo n means you just divide by the number, divide by n and the residue. So it is, mathematicians regard this is a difficult problem. This is called a discrete logarithm problem. And so this is one problem. This is the difficulty that helps us to save the situation. So in other words, suppose I give you a number a, and I give you a prime number, I give you a, usually n is a prime number. Then the function that a to the power b mod n, f of b. So you know a to the power b mod n, you know a, you know n, and finding b is believed to be difficult. This is what is called the discrete logarithm problem. Because you have to take a log if exponential is there. Okay, so this is one example of a one-way function. And there is, so this one is used in many places. Is used in many key exchange protocols. And so now another example is multiplication by two big prime numbers. Okay. Now big, I'm not going how big it is. There is some figure I put it, may not be correct. Is believed to be a one-way function, two primes, not more than that one is talking about. So RSA crypto system is based on this particular one-way function. So you take two primes, choose two primes, you multiply them. That's an operation that the computer is doing. But that n, which is the composition of two prime multiplication, finding given n, finding p or q is a difficult problem. So that's what is called integer factorization. So if you choose your primes properly, I mean, which is suggested or which has been checked that is difficult to figure out through this integer factorization, then you are safe. Knowing n, it is difficult to find what is p. If you know p, you can find out q. So RSA crypto system is based on the above one-way function, the first one. Of course, now this elliptic curve thing has come. I'm not going into that one. So that is a little bit more advanced. If one goes from here to what is called ECC, elliptic curve crypto system, all these algorithms can be put into that particular format. People who know elliptic curves, they know that how to, these things can be shifted. That is one more layer more safer compared to this using prime numbers. So most of the systems are now being shifted to ECC. All these credit cards and all other things, they have shifted it to ECC. Most of the sensitive documents are being saved now through elliptic curve crypto system. So RSA crypto system is based on this particular one-way function, that multiplication by two prime numbers, giving a composite number, that is easy. But knowing the composite number, knowing p and q is difficult. Reverting back is difficult. So usually this p and q are not too far away. That is being considered in this two prime number, this RSA system. It's just that p is just not too far away from q. So given n, which is the product of two prime numbers, it is hard to find the divisors. Okay. In other words, integer factoring is computationally hard problem. Just think about this little bit, give a little bit of breather and think that no one is saying that it is not possible. We are saying that it is hard. But just this belief that it is hard, a whole industry is running on that one. Lots and lots of people are working in this particular belief that, integer factorization, if you choose your primes P and Q properly, is a hard problem. Okay, so we don't have a polynomial time algorithm to factorize a given composite number. Okay, so that's the belief, and the whole industry is one industry is working on that one. So it's very funny that no one is saying that it's not possible. It's certainly possible. Someday it might be possible. Like there are these quantum computers. There's something called source algorithm, but it's still long way off. Okay, so this is some one-way functions that we talked about, and then this phi function. All of you know this Euler's phi function. So what is that function? The number of positive divisors. So phi m is simply the number of positive integers less than m and which are relatively prime to m. That means the GCD count the numbers less than n which are co-prime to m. So if it is a prime number, it's phi of p is p minus 1. So like you can calculate easily, phi of 9 is 6, and we assume that phi of 1 is 1. So this RSA, this thing comes from these three scientists. So this is Rivest, Samir, and Adelman. So this is the most successful implementation what they did in 1977, which is popularly known as RSA. R for Rivest, and S for Samir, and A for Adelman. So it's based on the idea that factorization of large integers into their prime factors is difficult. Because this is the algorithm, very simplistic algorithm. The naive one that I'm putting it in front of you, many layers, many generalizations of this has taken place to make it safer and safer and safer. Okay, so first you select two primes. I'm not going how to select. That's again another study in statistics and all, to generate large prime numbers. So that's another study that people do, that how to generate such primes. Not easy. So select P and Q. P and Q are both large primes, quote unquote, large primes. And then you calculate n. As I told you that n is simply P times Q. And phi n, it's a simple exercise from the definition that if it is a product of two prime numbers, phi of P is P minus 1. And if n is P times Q, which is it, then phi of n is simply P minus 1 into P minus 1. Okay, so this computer will do it very easily, calculating phi n, calculating n. Then you select an integer. How is that? So integer e is selected so that it is less than phi n, and it is co-prime to phi n. Okay, co-prime to phi n. That is because you need to have an inverse modulo that phi n, so that people know a little bit of group theory and all. So one can calculate the inverse of e. So d is simply the inverse of e modulo that phi n. So if n is a prime number, then it is modulo P minus 1. Okay, so what is your public key? Public key is n and e. N is the product of two prime numbers, and e is that integer. So your plain text is m, and what is your ciphertext? Ciphertext, as I told you, that is modular exponentiation. So m to the power e, and read it modulo n. So your ciphertext is C, and the plain text is simply you just multiply, you just raise it to the power d. So d and e will get cancelled out. Modulo n, they are inverse to each other, and then you get back your n. So you can take a simple example like select yours P is 17 and Q is 11, two primes. N is 187, and one can calculate that phi n is simply 17 minus 1 into 11 minus 1, which is 16 into 10 is 160. And let's choose e equals to 7, which is less than certainly phi n, and which is co-prime to phi n, so which is 7. And one can easily calculate that 7 is, the inverse of 7 is 23, modulo that 160. So your public key is like 7 and 187. 7 is your E and 187 is your product of two primes. And your private key is 23, 17, and 11, D, P, and Q. So suppose 88 is your plain text. You raise it to the power e, which is to the power 7, and you read it modulo 187, which is 11. So your public key is 7 and 187. And then your ciphertext is 11. It goes through that one. It reaches to the decryption point, and you raise it to the power inverse of e, which is 23. And read it modulo 187, 88 is back. Okay, so this is as simple it looks like, but it took so much time to really look into it. As you can see that the two things that is played, if you know the factorization of n, then you can get hold of this key. Okay, so this is about RSA a little bit, a very naive way. People who are beginning to look at it will see how it functions. But as I told you, that it is far more complicated than this, which is now prevailing. So what is a primitive root? Again, all of you would know that it's a generator. So primitive root modulo n, because this is the next protocol, the second and the last protocol that I will describe, will use this one. Not last, the suitcase problem will come back. So primitive root modulo n is any number g with a property that you take any number which is co-prime to n is a power of g modulo n. In other words, g is the generator of the multiplicative group of integers modulo n. Okay. So if you check, so that is again if you want to write it in a different way. So for every a co-prime to n, any number you choose which is co-prime to n, there is always an integer k such that g power k is a mod n. So g is a generator modulo n. For example, if you take 3 is a primitive root modulo 7, because you can get back everything. If you take power modulo, read it modulo 7, you can get modulo 7 all the numbers. So this is a key exchange protocol. So I talked a little bit about the RSA, and there is a key exchange, beautiful key exchange protocol of Diffie-Hellman. So publicly introduced the public key when they talked about it in 1976. And how is that? So how do they? So basically, one wants to exchange keys secretly. A key which has to be exchanged between two persons. So you choose a prime p, and a is a primitive root modulo p. Remember, we just described. So it's a generator of the multiplicative group of modulo p. So the key generation is the first thing. So what does A do? A and B, Alice and Bob. So select a private key. Choose any x A for Alice, which is less than p. Prime p is chosen. A is a primitive root modulo p. Okay, so once the prime is chosen, one can choose a primitive root modulo p. And how does A generate a key? Which is simply less than p. That is private. So xa is private. And what is public? Public is ya, which is a to the power xa. Xa is just that number which is chosen less than p. And reading it modulo p, a is a primitive root modulo p. That has been chosen by a. Okay, so that is xa and that is ya. Similarly for b, there will be xb and yb. Okay, so what b chooses another thing, nothing to do with xa. Any up to p, you could choose anything. So xb is again less than p. And what is the private key? The public key is simply a power xb modulo p. Okay. So what is the secret key of A? It is just, so you know, this public key YB is there. And what does secret key of A is simply YB to the power XA modulo P. Okay, XA is the select that the private key that A has chosen. YB is public, which is B. B is public key. So just A takes that YB, raises it to the private key that she has taken, or Alice has taken, raises it to the power XA and reads it modulo P. Similarly, B does the same thing. YA is public, and Bob just raises to the power XB, which is his private key, reads it modulo P. So that's it. This key, you can see that this is, if you look at pictorially, so XA and then calculates this public one. B does similar thing. XB is calculated, calculate this A thing, and then it is sent here. So K is the key that is sent to Bob. It is YA to the power XB modulo P, And what is YA? YA is X, A to the power XA, you remember. So A to the power XA, XB. So K is the key, what Bob gets is A power XA, XB mod P. And what this comes to Alice, you see, the same thing, that YB, that key which is generated by Bob comes to Alice, and Alice to the power XA, and so both have the same key. See? So this is what Diffie and Hellman's idea was there, and you can see this is easily one can implement that one, and this is how this Diffie-Hellman key exchange, the basic one, the key exchange takes place. That's how they get the key without revealing. And as I told you, that modular exponentiation is one-way function, so that's being used here. Of course, all these things have to be chosen properly. I mean, keeping into mind that how big that prime should be. So let's come back to the suitcase problem, which we had given. I'm sure that all of you have already solved it, but it's nice to just come back to that one. So remember, the problem was Alice has a suitcase and a lock and a key. Bob has a lock and a key. It's not compatible. And Alice wants to send the key to Bob securely. How that can be done. Okay, so this is here what we have solved. I'm sure that Alice puts her message in a suitcase and puts her lock into it. Puts her lock into it, sends it to Bob. Bob has no key for that one, so Bob can't open it. So what Bob does, Bob puts his own lock into that one, right? And sends it back the suitcase to Alice. Now Alice has the key for her own lock. She just removes that lock with her key, but still the suitcase has one lock, you see. It's still safe. It goes through again to Bob. Bob uses the key of his lock, which is known to him, and just opens it. Okay, and reads the message. So all through, you can see that all through the passage through this is locked. The suitcase is always locked. So if you choose your locks properly, nobody will be able to open it in between. And the message will be delivered. So this is pictorial. If you see, the locks are being put. It goes to Bob. Bob has a lock. Bob puts it. So two locked suitcase comes back to Alice. Alice uses her own key, and her lock is being opened. Now it goes back to Bob with one lock, and Bob has the key. So Bob gets back the suitcase and opens it. And if you want to put it in a mathematical format, you already have seen Diffie-Hellman key exchange problem, so you can easily do it by yourself. So choose again a prime number and choose a random private integer. So this is what that both Alice and Bob need to have a lock and a key. So this EA is the lock for Alice, and DA is the key, which is the inverse of EA. And similarly for Bob. So if you see pictorially, you will have this first cipher text, that M is the text, and Alice raises to the power EA, reads it modulo P, and sends it to Bob. This is one lock. That's EA is the one lock. And then Bob doesn't have the key for the inverse of EA is not known to Bob. Bob can't open it. So Bob, what he does, he raises to the power EB. That's the key. That's the random integer that Bob chose. Now this is two locks are there. As you've seen on the way, there will be two locks. It comes back to Alice, and Alice knows has the key of EA. So she raises to the power DA. The computer does that one, and then DA and EA negates each other. So now there is one lock only. And it comes back to Bob again. And obviously Bob raises to the power DB, which is the inverse of EB. And EB and DB gets cancelled and gets back the M. Okay, so this is what Massey Omura encryption. So if you take, suppose your P is 101, and that prime that has to be chosen, and you take that suitcase 111, and then chooses that 7 is an integer less than 100, 5p, which is certainly, and is co-prime to 100. So 5p is 100 and 7 is co-prime. So it is raises to the power 7. It's 871. So it is 871. Similarly, Bob chooses the number 3. So 871 goes there. And Bob raises it to the power 3. That is the lock that Bob has. So it is 311. You have to read modulo 100. And then inverse of 7 is 43. So Alice raises to the power 43. 7 and 43 cancels each other, 631. And then Bob raises to the power 67, which is the inverse of 3, and gets back 111. Okay, so this is basically a very simple way, but this is how this mathematics is being used to create the lock and key. But finally, it has to be put into a mathematical into a algorithm, and that's how it functions. Okay, so this is what I wanted to give you a little bit about this basic construction of crypto things. And so this is part of formulating a protocol using mathematics. And now you would ask that how does the other side works, like how to break these systems. Like as you saw that if you can break n, if you know prime of it, then you can break the system. So how do integer factorization? What are the ways to factorize big integer? That's the next few minutes that I have left with. I'll just tell you. So direct attack on RSA, if you can factorize this n, if you know its component, one of its components, so that breaks the system. There are these methods, mathematics. The sieve of Eratosthenes doesn't work now. Trial division, which is also very naive. There is called quadratic sieve. There are elliptic curve methods. There is number field methods, which I'll talk very little. And there is so-called Pollard row and P-1 method. Then there is continued fraction algorithm. Then there is this last one is Shor's algorithm, as I was talking about, quantum algorithm, which theoretically breaks, but we are yet to have quantum computers which can do that. So trial division and the sieve of Eratosthenes, as you can see, it's very naive, very old thing. So it works up to 10 to the power 12, which is certainly not enough. We need far more sophisticated techniques. So what is the objective? Objective is that you have a composite number n, and you want to find a non-trivial factor of that one. Okay. So n1 and n2, certainly it's less than n and bigger than 1. So primality, then if you can find out, then you test the primality of, there is something called primality test. And if it is prime, you got it. If it is not, then you keep on doing this, trial divisions. Okay, so what is Pollard's P-1 method? Just to give you a little idea that how that works and how you can resist that. Okay. So n has to be factored. So let's take B some upper bound of some smallest factor of this n. Some upper bound you have to fix. You take A is, let's choose A equals to 2, and you run your J from 2 to B. Okay, B is an upper bound which is fixed, and you do every time you choose a J, you raise it to the power J. The n is known to you, and then you try to find out this GCD of A-1 and n. Every time you do that, and if you find a non-trivial GCD, then you return that B, because then you have a factorization. If you're not, then you fail and you start again. So that's how this Pollard's P-1. Why it is called P-1? What is the complexity? Complexity means is that time that it takes and the amount of storage that it takes. Algorithm is polynomial in the size of B. So if you choose your B is small, obviously, as you can see, the chances of getting factorization is very less, low chances. And for large B, you need approximately square root of n times trial division, which is pretty, I think, quite a lot. So this method works when n has a prime factor p. So n has two prime factors, p and q. So n has a prime factor p such that P-1 only has small factors. So this one can check that this method of P-1 of Pollard, it works only if you have chosen your n, which is consisting of two primes p and q, which one prime has, P-1 has only small factors. P-1 will be an even number, and so it will have just small factors. Otherwise, it doesn't work. So if you want to get resistance from this factorization method, you have to choose your primes properly. So that's why 2p, you choose a prime which is 2p plus 1 is also a prime. This is something called safe primes. I'm not going into that one. And one can see easily that if you choose such a p and q, then your n will be resistant to this polar p-1 attack. Okay, so then because it needs p-1 only has small factors where it is not happening here. Okay, so this is a small thing. People can study more if they are interested into this breaking algorithms. Then there is this row method which was introduced by Lenstra around 1980. So suppose p is the smallest prime factor of n. Then there are choose two distinct integers x and x prime such that modulo p they are same. And then look at the GCD of x minus x prime. So you have chosen two distinct integers x and x prime. Look at the GCD of x minus x prime, x minus x prime, and n. So this is between p and n. Now you have to define a random set x, which is Zn is integer modulo n, and take a random set x. X needs to be bigger, so n is also very big. Zn is big, and compute the GCD, which you have to do it x minus x prime and n for every pair x and x prime coming from this set x. Okay, so if there is a collision, that means if really it happens, the GCD comes out, then you get a factorization. And by what is called Barthe paradox, chances that there will be a collision is about 50%. So this is how it is chosen, that you choose a polynomial, and how you choose that set x that has been described by Lenstra, that you choose x squared plus small a, and choose a x1 and consider this set x1, x2, xm such that xi and f of xi minus 1, fx is x squared plus 1, so square plus 1, and that is your xi modulo n. So thus if your xi is xj, look at that, x should be equal to x prime modulo p. So if your xi and xj modulo p are same and I and j are distinct, then that would imply that fxi is also fxj. And thus xi plus 1 is congruent to xj plus 1, it will happen and there will be a collision. Okay, so if you build the graph of these vertices of in Zp and the edges between xi mod p, so it takes a shape of a row. Okay, so that's why it is called, the graph will look like a row, so that is called Lenstra's row method. And if you take j equals to 2i, you can see by this algorithm how this collision, so collision means there will be a GCD of x minus x prime and n. So you can choose x is x1 and you can choose your x prime, fx is like x squared plus 1 modulo n, and look at the GCD of x and x prime and n. See p is 1, you go ahead and do it if the GCD is co-prime, keep on changing x to x and fx, x prime to fx prime. And if your prime, if the GCD comes out to be n, then you return it is failed because then no collision is happening. Otherwise, you return that p. And if you keep collecting that, it will take a shape of and there is a 50% chance that you might be successful in finding a prime factorization. So so many iterations are needed if you want to find a p, square root of p times. Now the last thing that I want to point out to you is called the general number field sieve. So people may not have idea about number fields, as is the students who was undergraduate and all. So we have Q, and if you take any extension of Q, like a vector space over Q, it's a finite extension. So there's a finite dimensional vector space over Q. So we called such a extension of Q, a finite dimensional extension of Q, as a number field. Okay, so like Qi, if you take it, it's a degree 2 extension. So you have a basis like 1 and I, which generates that one. So it's a degree 2 extension, the simplest that is possible. So Q square root of D, like D is square free. So these are called quadratic extensions. So you can see how sophisticated mathematics is being used to factorize an integer. And this is the best known method that we have right now. And it has factored very big numbers, RSN numbers. People got awards for that. So the number field sieve has evolved. So general number field sieve. Sieve means you have to sieve out those numbers, what you are looking for in 6-degree extensions in the ring of integers. To find a better ways of factorizing, because those are not very efficient. Composite numbers having 2 prime factors. Okay, they are called semi-primes. So we are always interested in factorizing n, which is a compositum of 2 prime numbers. So they are called semi-primes, almost primes. If the number is big by all those methods, it seems it is intractable to factorize that. So that's how we used to think that it is safe. You know, our system is safe, we don't need to bother too much. But once this number field sheet came up, then people started breaking those big numbers, and it becomes unsafe, those RSA systems. So we have to go on seeing that how much this GNFS can do, how big primes it is breaking, how big composite number it is breaking, and then you have to go one step ahead. So you need to find bigger primes. And that's how you remember in 2018, December, the largest prime was discovered. So people were thrilled. And many people are very much interested into searching for primes, big primes. Lots of people work on that. Okay, so that is why here, because if you find that the two composites P and Q that you have taken, and that has been broken with that number, then you have to choose your P and Q bigger. But how to find large primes? You take a large number, then how to test that whether it is a prime or not? Well, I hope you are understanding some of the difficulties that is involved in that one. So assume n is composite. Composition can be checked by Miller-Rabin test. So I'm trying to explain a little bit to you what is this GNFS. So we did a DRDO project of factoring big numbers when I was at HRI, and we used this GNFS method. So it is composite and non-divisible by small primes. Certainly not divisible by small primes, because then you can use one of those things to figure it out, like what I told to break it. So basic idea behind all algorithms with sub-exponential complexity, don't bother, that's a terminology that is used, that is quite difficult to break. To start with a pair of natural numbers, x and y, such that x square plus x square is congruent to y square modulo n. So n you have to break. So look for two natural numbers. That's what I was telling. Some sieving has to be used. So you have to find such integers x and y so that the squares are same modulo n. And you have to check one more condition, that GCD. So x square is congruent to y square mod n. So x square minus y square is 0 mod n. So x plus y into x minus y is 0 mod n. So that is x plus minus y and n. You have to look for the GCD. The GCD will be lying between 1 and n. So you have to choose such integers, pair of integers. If true, suppose the GCD is bigger than 1, then you have got a non-trivial factor, and we pick that pair. Okay, so you have to pick those pairs. Okay, so suppose n is odd composite number, which is not a power of a prime. Suppose this. So suppose your n is odd. Certainly it's a composite number. We know that. We can test it. For any random pair of integers xy with xy between 1 to n minus 1, such that this happens, the GCD of xn, GCD of yn is 1, and x square is congruent to y square mod n. Then the probability that the GCD will lie between 1 and n, that means you have a non-trivial GCD, is at least half, 50% chances are there. So you have lots of such integers are there, but you have to sieve it out, that which are those integers which has this property. Once you have that, then you can find a factorization through this method. So Dixon's algorithm and that of quadratic sieve is not conducive for factoring large integers. So this GNFS is the best known method so far to factorize large integers. And the main steps involved in this one is that you have to choose a polynomial. As I told you, we use a 6-degree extension for big numbers to factorize. And to find an irreducible polynomial of 6 degree, that's the first thing. Properly you have to choose it. Then you have to go to the field extension. You have to go to the ring of integers there, and you have to sieve out those pair of integers, you see. Lattice sieving that is being used there. And then you have to get back those xy. You should be able to take square roots. And so these are three steps that is there. So in the first module, an appropriate polynomial is selected depending on the size of integer n, which is to be factored. Okay, so depending on the size, the degree of the polynomial or the degree of extension has to be chosen. So RSA 600, which was broken, one needed a polynomial of degree 6, as I told you, which is monic irreducible polynomial over Z. You attach a root of that one to get a degree 6 extension over Q. and then work in the ring of integers, as I told you. And then use lattice sieving. And this is the most time-taking one to really look for those particular, and linear algebra is heavily used here. Just imagine you want to factorize the number, what kind of mathematics is, lots of algebraic number theory, and then you need lots of linear algebra, sieving for this second part. And then the last step is the square root module. So 3 modules are there. Choose a proper polynomial. You have to go into the field extension, look into the ring of integers there, and then use this what is called lattice sieving to sieve out those pair of integers xy with those particular properties. And then once you have got with those particular properties where non-trivial GCD is there, then use your square root method, which is again non-trivial, to find those x and y. Here in this step, the square root of the above integers are derived using heavy algebraic number theory. Okay. So this is a little bit that I wanted to tell you, that starting from the very beginning, that how the crypto were developed in such a huge, mammoth way now, what we see it. And this is just a little try from my side to give you a very naive way that how it functions. I'm sure many of you will be interested in your future, those who are young students, to really contribute in this area. In a country like India, we really need lots of bright students like you to come to this arena and contribute to the safety and security of the country. And the government of India and every government, they are very generous. If you have a crypto project, immediately they sanction it, and they really get impressed if you can do some such work like integer factorization, or producing protocols, making things safer, using mathematical tools. So that will be the challenge for the next generation, to really produce more and more safer protocols. Thank you so much for your attention.
Thank you, sir. That was really an amazing talk, and especially for the fact that you started from classic crypto puzzles and then came to RSA as well as field sieving. So that was a really nice overview. I hope a lot of people in the audience
Thank you so much.
will really be motivated by this. I will also like to mention that Dr. Chakraborty actually works a bit with class groups as well. He is also working on cryptographic techniques related to those. He organizes class group conference every year, which is a really nice thing. So I would like take in questions right now from the audience. So there are some questions in the chat. So can I read them out?
Sure.
The first question is from Mihir. He is asking, in RSA, why is the private key written in the form of D, P, and Q and not D, N?
Yeah.
So he is asking, why is the factors P and Q required separately?
Somehow this Wi-Fi is not very good here. Sir, can you tell the idea about the probabilities coming at least half for the GCD to be between 1 to n? Yeah, I mean, it's a result, you see, and there is a theorem and a proof. So if you are interested, you can really go into the, the actual, it's just a very naive way. I'm not an expert really into those things, but we generally assume the result. So how it comes, that one has to really see the proof. But I don't think I can immediately explain. I don't know the proof really, that how the probability becomes half. Okay, so sorry about that. And I think you can, it's a good question that you should look into the proof of that. My slides will be there. So you can go to the, I think it's maybe Ledstra's one or Gautier. You should know more about, if you are interested in integer factorization, each of the method I told you, you should go through that one and see how that helps breaking the system. Okay, so 50% chances are there. You can take some examples also to check it. I didn't do it because I didn't really mean to go into the integer factorization, but just added at the last moment. Thank you for that question, but it's a good question. You should look into the proof. And the second one is RSA algorithm. Why is the private key written as DNQ and not DPQ? Yeah, I mean, it's good observation. It is just private key because we know what is P and Q, just to show that it's a private key. Private key in the sense that only you can see, so you know what is P and Q. It's not, you can write is as well as a D, but if you write N, then N is public one, you see. It's the product of P and Q. So to show it is private, the factors of N are also written. That's it. Because if you write N, then N is already public. So if you want to really put it down that what is your P and Q, when you write an algorithm, you have to really write that P and Q. Because the algorithms are being fixed by choosing this P and Q, and they are huge prime numbers. So only for that, to show that it is private, not that others are seeing it, and N is actually, as you see, that N is a public key. Yeah, so there is another thing that to read about algorithms, to talk about algorithms, I can tell you that you can, there is a book by Washington, Larry Washington, which is called Elliptic Curves and Cryptography. So as I told you that most of these things are now shifted to elliptic curves. So maybe if another time such moment comes, I will give a talk on elliptic curve crypto system, where I can define elliptic curves and really take you into a couple of algorithms like this, where it is written in terms of elliptic curves. So you have that book of Larry Washington, and there is of course a basic book of Koblitz, Neil Koblitz, Introduction to Cryptography. So there these algorithms are mentioned there. So Koblitz, you can have a look at it, and you can, if you want to read a little bit advanced things, then you can look at Larry Washington's book, Elliptic Curves and Cryptography. Okay, I think that's all the questions that I could see.
So there is a new question from Krishan.
So how one should detect what cipher algorithms actually have been used while breaking a code, that is submission or substitution or permutation or using a public key. Yeah, you see, you will see that wherever you are doing some transactions, you will see what kind of encryption they have used. They write that one. That's a patented kind of thing. You can see that they write it here there, and then you have to read about it, and then that's how they do it. And mostly these are some examples I gave you, but these are the one-way function that is being used everywhere. Not many one-way functions are known, like modular exponentiation, prime product of prime numbers, and elliptic curves. You will see that group algorithm that has been used. So these are the only one-way functions that one has, like discrete logarithm problem. So if you can break discrete logarithm problem for bigger things, you will be able to do these things. Like most of these protocols are based on either product of prime numbers or discrete logarithm problem and modular exponentiation. So if you know how to do it, how to break it, you will be able to break it. But they do write, whenever you do some transactions, you will be seeing that they're writing that what protocol, what security system they are being using. So this substitution, permutation and all, they're not there. They're very easy thing, but you'll be talking about like discrete logarithm problem, that what are the ways to break a discrete log problem, how to solve, and integer factorization. These are the two main things that is there. Yes, that's what I'm saying, how to break codes. Yes, that's what I'm saying, that how to break codes without knowing what the system is. But I'm saying that breaking codes means you need to find like how to factor those big prime numbers, or how to find this discrete log problem, how to solve the discrete log problem. And if you go to any standard thing, you will see it's not difficult. Those who are in theoretical computer sciences, that how big those that integer n that is been used from the protocol that is being applied there. But you can see that they write what protocol they are using it. Verizon Safe and all, you can see that you can go to Verizon site. Yeah, so I understand your problem, that without knowing the protocol, how I know how to break it. But as I'm telling you, the core thing that is being used is about discrete log problem and what is called the integer factorization. So if you know how to do it, if you have an algorithm to break integers, you are done. Overnight, you are very, very famous.
Yes, thank you, Dr. Chakraborty again. I guess we don't have any more questions right now. So we'd like to thank you again, and we hope that in future we'll get you for more advanced topics in your research area. I would like to ask if anyone is willing to turn on their mics. We will give a small clap for the speaker.
Thank you so much. It's really a great pleasure. Hope to see you guys again.
Yeah.
Thank you so much. Stay safe. Bye-bye.
Yeah, thanks.